Good morning everyone and welcome to today's webinar, the Advanced Modelling Features of LimitState Ring, which is the 12th in our series of webinars which discusses the features of LimitState products. To introduce myself, I'm Tom Pritchard, your host for today's session, and I'll be passing you over to our speaker today shortly, who is Professor Matthew Gilbert. I'll also be rounding up at the end. Today's webinar will provide you with an insight into some of the more advanced features of our masonry art analysis software, LimitState Ring, such as the ability to model local defects and support movements. The main section of the webinar will run until approximately 10 AM UK time, and we'll have about 5 or 10 minutes at the end for questions, which you can post at any time via the chat functionality, which is present in the webinar interface in front of you. We'll try to answer as many questions as we can, but sometimes this isn't always possible, so our apologies if we're unable to get around to yours. We will, however, follow up on any unanswered questions after the webinar is finished. If the webinar does spark any questions later on, please do contact us on info@limitstate.com and we'll be more than happy to answer the questions in detail for you. So without further delay, our speaker today is Professor Matthew Gilbert, who is the LimitState Ring Product Manager, and I'll now just pass you over to him.
Thank you very much, Tom, and thank you very much to everybody for joining us today. Okay, so title of the webinar, Advanced Modelling Features. It could alternately be titled The Less Well-Known Modelling Features of LimitState Ring. So what we're going to cover, first of all, I'll just give a bit of background both to the company LimitState and also to the business of analysing masonry arch bridges. I'll then move on to the advanced modelling features that we're going to cover today. Three in particular. Firstly, modelling local details of a bridge. Secondly, using the support movement functionality. Thirdly, using reinforcement in the model. And then finally, we'll wrap up with some conclusions. Okay, so first of all, just say a few words about LimitState. Spun out from the University of Sheffield in 2006 and focusing on commercializing academic research. In other words, making research methods developed in the university available to a wider audience. The key areas of interest are applying optimization technology to provide rapid and easy to use ultimate limit state analysis and design tools. And as a company, we're able to fully support the software as well as focus much more than you would from an academic environment on ensuring that they're easy to use. Okay, so if we just step back and look at the ultimate or collapse analysis tools that are available to engineers, basically they fit in two camps. Either hand calculation camp, where we might now be talking about tools which are embedded in a simple program or spreadsheet. So that's one end of the spectrum. And then at the other end, we could use, for example, something like non-unifying elements or discrete elements in order to do our analysis. The problem has been historically there's been quite a large gap between those two types of tool, and what we're focusing on at LimitState and springing from work carried out at the University of Sheffield is developing what you might think of as mainstream tools which sit in the middle, which use numerical rigid plastic analysis and bring many of the benefits of hand calculations, but also many of the benefits of advanced methods in the sense that you can apply the techniques to arbitrary geometries and the like. And we could be talking about geotechnical problems, as shown on the previous slide, masonry problems, as you can see on the current slide, or, for example, reinforced concrete slab analysis problems, which you can see now on screen. And in fact, those three categories correspond precisely to tools currently available in the LimitState product range. So we have LimitState Ring, which is of interest today. LimitState Geo for geotechnical analysis. The latest addition to the list of products is LimitState Slab, which is designed to systematically automate the yield line method analysis for reinforced concrete slabs. And these tools are used in many countries worldwide by many major organisations. And here's just a little selection of them from our website. A is down as far as B, so big companies, AECOM, AMI, Arab Atkins, and so forth. So just a few words about LimitState Ring before we get into more detail. It's actually been around in its current form since May 2007. Built on software that the University of Sheffield made available, and as I mentioned, used by many major companies. The key feature of the software is that you can very clearly visualize the predicted mode of response of a structure. So you can see the collapse mechanism, and you can also see the line of thrust or zone of thrust and hinges when you're doing analysis. So the idea is that it gives you as the user a better indication of what's going on than with many tools. LimitState Geo, geotechnical analysis software, launched 2008, uses a method called discontinuity layout optimization, which can be viewed in a sense of as extending the rigid block method that LimitState Ring uses, so that you can also treat continuum problems such as soil. And again, companies using that worldwide. And then the most recent edition, launched earlier this year, February 2015, again using discontinuity layout optimization, is LimitState Slab. And what it allows you to do is move away from the business of guessing a collapse mechanism and manually iterating towards the potential collapse load, to actually allowing the computer to identify that for you directly. And there are already a number of companies, large and small, using that software. Okay, so a bit of background to masonry arch bridges. Apologies if you attended the previous webinar in the series. This is a few slides which are common with that previous webinar. But I just want to get across the sort of big picture. First of all, there are many bridges in service worldwide. We estimate around 1 million spans. Vast majority of those are more than 100 years old, and clearly they need to be assessed regularly. How do they stand up? I think the most sort of illuminating work in this area was carried out several hundred years ago by Robert Hooke, who said if you have a weightless chain or cable and you suspend from that cable the voussoirs that you're going to use to build your masonry arch from, and then you look at the profile of that weightless cable, you invert it, and you find that you can fit that within the thickness of your finished masonry arch, then you can be confident that your arch will stand up. That line is now the line of thrust or line of compression, and as you might expect, because we're dealing with a statically indeterminate structure, there are a number of possible lines of thrust that you can have. The key point to make, however, is that there is a limiting line of thrust which corresponds to the maximum load that the structure can carry, and we can actually find that, and we actually use optimization in LimitState Ring to find that in our case. So if we then apply any more load, we will get collapse. So we actually have a state where we can just fit a line of thrust within the masonry, and that will actually also correspond to the point at which we just get a failure mechanism or collapse mechanism. So, points to make. Many possible lines of thrust. If the supports move, then we can identify a unique line of thrust. So that changes things a little bit. And actually, in many cases, you will see that abutments have moved outwards slightly, either immediately following removal of the centering or sometime later. And we can use support movement mode in LimitState ring to explore this scenario. At collapse, however, we have a single limiting line of thrust or equilibrium state. And at collapse, we can therefore relatively easily find the load required to cause collapse. And that's the normal mode that those of you who are familiar with using LimitState ring will have encountered. So just bring your attention to the fact there's two distinct modes in the software. How do we find the solution? Well, if we think of all the potential lines of thrust as being permissible equilibrium states, then of all those states, we use optimization to find the one corresponding actually to the maximum load factor. And in terms of maths, that boils down to maximizing the load factor subject to equilibrium constraints and also yield constraints. So if you think about the fundamental sort of building blocks, excuse the pun, of the model, we have blocks where we are enforcing equilibrium, so equilibrium in the x direction, the y direction, and also in the rotational sense. And then at the contacts between blocks, we have forces or stress resultants. So we have a shear force, a normal force, and a moment. And those forces at the contacts we can limit according to material properties. So for example, the bottom one of these two constraints you can see in the lower circle or ellipse is enforcing the shear limit. So the shear force cannot exceed the coefficient of friction multiplied by the normal force. The upper one is actually a rocking constraint, which says that the moment can't exceed the normal force times half the thickness. And that, in this particular case, is assuming infinite compressive strength. It looks slightly different if we include a limiting compressive stress. But the main thing to get across is that in mathematical terms, this is a very simple optimization problem to solve. So we can solve it rapidly and efficiently. We don't come across many of the problems that we might do if we were, for example, using incremental methods associated with finite elements, or non-linear finite elements, should I say. Okay, so we've talked about the masonry and the arch. Of course, that's far from the full picture. We actually, generally speaking, will backfill around the arch barrel with soil. And the way we model that is by firstly assuming dispersion of the live load through the fill. So instead of having a small loaded length, we have a much longer loaded length by the time the loading gets down to the barrel. And secondly, we use backfill elements to model the passive resistance offered by the soil as the arch tries to sway into the soil. And we've got on the slide, you can see now backfill elements off or on. They're off when the arch is moving away. They're on if the arch is moving into the soil. Another way of saying that is that actually we're neglecting active pressures which are relatively small. We are modelling passive pressures which is considerably larger. And another way of describing that is in the figure in the top right, which describes the mode of response of the backfill elements. How does that work in a real bridge? Well, in a real bridge we might have multiple spans. So the loading is dispersed through the fill. If it's a railway bridge, then it will be dispersed in a slightly more complex way because we assume that we have loading through sleepers and typically 3 sleepers per axle are assumed to disperse the load. We then move the load moves down onto the arch barrel. Backfill elements can be on or off, as I mentioned earlier. So here we can see that above the first pier we have mobilization of passive soil pressures, but we don't have that above the second pier. And here we've also got backing elements. So backing elements can be considered to be stronger backfill elements where we have a larger resistance, and they're used to model masonry or concrete infill in a bridge of this sort. You can also see the other bits and pieces in the bridge, so hinges, a thrust zone. The thrust zone is the thickness of the thrust zone depends on the amount of or the thickness of the masonry required to carry the force, and that clearly depends both on the magnitude of the force and on the compressive strength of the masonry. Okay, so the first advanced modelling feature that I wanted to cover in today's webinar is the business of modelling local details of a bridge. Now, many of you will have already be familiar with this one, some of you won't. So the key thing to note is that in limit state ring, we can either model global details, span, rise, global masonry properties, or we can dive down into more detailed areas. So we can, for example, model specific details of 1, 2, 3, however many blocks or contacts that we want. And the way we do that is that we select blocks or contacts and then we amend their properties in the property editor on the right hand side. So here we can see, I don't know how clearly you can see it, but it's basically the properties for a block, and we can, for example, locally change the unit weight or the fill stress applied to that block. And just as a way of demonstrating this functionality, I'll just look at some laboratory arch ribs that were tested some years ago. The interesting thing about these tests was that we looked at various different inter-ring details for them. So we actually tested 4 arches. The first arch had fully bonded arch rings. The second arch had unbonded arch rings. Arches 3 and 4 had partially bonded arch rings. And I'll show you how you can model each of these scenarios. Okay, so in fact, if we go straight to the partially bonded case, just so you can see what I'm talking about, what we actually had, certainly in the case of arch 3, was a case where we had headers only placed at a limited number of positions in the span. So we actually had 1, 2, 3, 4, 5 headers, and then the arch rings were unbonded between those headers. So what I'm going to do is I'm going to start the software. Okay, so actually what I've got is a model of a standard bonded arch, if you like. It's slightly different to usual, however, because we, in this particular case, have set the backfill unit weight to be 0. So in other words, we don't have backfill, and also we have locally focused the load on a particular point of the arch. And if I click solve, then you can see very easily that we get a standard 4-hinge failure mechanism. And the collapse load for this this bridge is 4 kilonewtons, which is actually very close, as we'll see shortly, to the experimental collapse load of 4.2 kilonewtons. What I can do, however, is I can change the geometry so that instead of modeling only a single ring, I can actually model this arch as 2 rings. So what I'm going to do is I'm going to model 2 rings which have thickness which add up to the thickness of the original arch barrel. And you can see now that we've got contacts not only radially but also circumferentially as well. And if we click solve there, then you can see we've got a very significant reduction in the collapse load. Actually here the adequacy factor and the collapse load are the same because I had a unit load applied to the structure. So what we're saying actually is that whereas the previous bridge required 3.99 kilonewtons to cause collapse, this one requires 1.47 kilonewtons. And what you can see is that we've got a line of thrust in the bottom ring and also a line of thrust in the top ring, and also dispersed hinges, which are actually very similar to what we see in the lab. Okay, so what I'm going to demonstrate now is actually setting local properties. What I can do is I can effectively transform parts of, I can actually insert headers into the structure. So if I select the contact in the location of the first header, and what I can do is in the property editor, I can say that actually there is no hinging and there is no sliding. And when I've done that, you'll see that actually the color is slightly changed. It's just to provide a kind of an indication that we've got custom properties there. So now I can set the next one. Let's just count round 1. So this one is be the next one. Again, I can do the same. So no hinges, no sliding. We've got one at the crown. And then we've got in the same symmetrical locations at the other side. And the last one, 1, 2, 3, 4, 5, 6, 7, 8, 9, there, I believe. I'll do the same. So now we've got effectively our headers built into the structure, and maybe I'll just turn the thrust line off because it's a bit distracting. We've now got a very significantly different adequacy factor stroke collapse load of 3.17, which is more than double what it was before. And you can also see that where I've put the headers, we have no deformation effectively between those the top and the bottom blocks. And if I go back to the slide, then we can see actually that the load that we got, 3.17, rounds up to 3.2, is very, very similar to what we found experimentally. Similarly, 1.47, which is what we had for the previous one, is very similar to 1.5, and the first collapse load for 3.99 is very similar to 4.2. So you can see that we are effectively getting very similar results in the LimitState ring software compared to what we got in the experiments. Just out of interest, that the last arch 4, was the same as arch 2, but instead of inserting headers, we actually put steel plates. That gave us a slightly different mode of response. We actually had slightly a larger zone over which the connection between the lower and upper ring was made, and actually the experimental failure load was slightly higher, but still pretty close to the modelled result. And then moving on to a more practical example. This is a culvert, short span. Hammer survey has indicated that there's lots of ring separation across the bridge, although that doesn't extend all the way into the abutments. So the question is, can we model that appropriately in the software? So this gives us another view of that, where we've got a ring separation which covers most of the span in actual fact. If I go back to the software, we've got that one brick house. This is one I've already set up, and the way we've done this is by having just a frictional interface between the upper and lower ring in the central area, and then we've actually glued the blocks together in the areas you can see in purple. In this particular case, what I'm going to do is I'm going to run the vehicle across the bridge, and so what it's doing now is going through load cases. Each position we have a computed adequacy factor, and the lowest adequacy factor in this case is at load case 17, which is the one that you can see on screen, and we have a very low adequacy factor of 0.3. This in particular is with quite a conservative effective width and various other things, but it nevertheless is indicative of the weakness of this structure. What you might want to do is, for example, at this point, see what the benefits might be of stitching the upper and lower ring together, and you can explore that as you can imagine using the software. Okay, so I'm going to move on now to the second advanced feature which I wanted to cover in the presentation, support movement mode. Support movement mode is really useful for doing two things really. One is to help you understand how the structure is carrying service loads effectively. So if you have a structure where you've got some evidence of slight support movement, then, as I mentioned earlier, it transforms the structure to a statically determinate form, and then you can move loads across the bridge, and the load paths that you see in the model are likely to be very similar to the load paths that are active in practice. And the second thing that you can use this feature for is to diagnose the likely cause of existing crack patterns. So if you see cracks, you can move supports around to try to identify what the likely underlying cause of those crack patterns is. How do we do the analysis in this case? Well, the formulation looks a little bit different. So instead of finding maximum load factor, we're actually finding a minimum energy solution or minimum energy done by the supports, and other bits and pieces in the formulation are also changed accordingly. In terms of the actual software, what I'll do is I'll just set up an example. So let's, for example, set up a highway bridge. I'll make sure it's a 2-span highway bridge. So, for example, I can apply a support movement to an intermediate pier. I'll make this intermediate pier, say, 3 meters in height. I'll keep the same geometry for span 2 as span 1. And I'll just use the defaults for most of the other parameters in the model. What I will do though is I will select a vehicle. Let's suppose an EU triple axle vehicle, and I will use that in the model. So here we have a simple 2-span bridge with loading on the first span, and if I click solve, then I get a predicted mode of response. So it's actually got 7 hinges, 3 in each of the spans, and 1 at the base of the pier. Okay, so this is a standard analysis. However, what I can alternatively do is move the load off the bridge, and in normal mode, then I get no solution. So the software doesn't know effectively what the thrust line profile should be in the absence of a support movement. When I go into support movement mode, that changes. So what I'm going to do is go into support movement mode, and there's a little wizard, and the first thing I'm required to do is to pick a support block to settle. And what I could do is I can choose well, any of the supports that I've got in my model, and I can put arbitrary relative displacements. What I'm going to do in this example, however, is simply assign a vertical downward movement of 10 millimeters of the intermediate pier. And if I now click solve, then I do get a solution, and you can see that that solution is associated with the downward movement of that intermediate pier. In other words, I get the thrust line and the expected hinge positions for that scenario. And what I also get is an energy or a work, which probably isn't of too much interest, but that's just a byproduct of the method of solution. So what I could do if I was interested in diagnosing the likely causes of cracks is adjust the relative support movements until I get crack or hinge locations that coincide with those that I see in the field. And we'll come to an example of doing that in a second. Another interesting thing to do is to actually see what the influence of a vehicle is on the locations of these hinges. So if I traverse the vehicle across the bridge, you can see that actually those hinges change location. And this could be a wake-up call if you have service loads which are effectively causing joints to open and close on a very regular routine basis, because that's likely to lead to an accelerated breakdown of the material forming the arch and likely reduction in the lifespan of the bridge. So the key thing to remember here is that the vehicle is now not factored. So the vehicle loading is not factored. If you want to apply a load factor to the vehicle, you need to assign that manually. In other words, the whatever vehicle weight that you specify is that's assigned in the support movement mode. Okay, so let's go back to the analysis. Sorry, to the slides. The next slide shows a view of a viaduct that's actually approaching the River Seine in Paris. It's actually the first problem that I assigned, that I applied this functionality to. What actually happened is that the timber pile supporting a number of these piers appeared to have rotted, and there was relative settlement. And that relative settlement led to quite severe cracking. It's quite difficult to see from a distance, but it's shown in annotated form on the slide you can see. And the first model that I developed using approximate geometry looked something like this. And the key thing is that the hinge positions that I got from the model very closely approximated those that we saw in the field. To build this model, what I'd assumed is that we have backing material above the piers up to approximately the level that you can see on the slide. So that appeared to be a reasonable model of the structure. What I then did is I developed a new model with a reduced amount of backing above each pier. And you can see that led to a change in the predicted hinge positions, and actually to hinge positions which are more different, or actually quite different to those that we see in the bridge in the field. So in other words, the previous model was almost certainly right as far as the amount of backing. And that gives rise to quite an interesting observation, that actually you can treat a settled bridge as an opportunity, because if you get a good match between the model and your bridge, then probably the details that you've input into the model are actually largely correct. And if you have the same kind of bridge repeated on other stretches of the line or road, then that effectively has given you an opportunity to develop a more informed model for those other bridges if they were constructed at the same time with the same materials. So in other words, effectively it can be considered as like a free lab test of your batch of structures, if that makes sense. Last one before I move on to the next feature is a bridge that's been subject to mining subsidence. You can see quite severe distortion to the parapets because of the mining subsidence. And here we have the model that was developed, and In many cases, the model and the bridge in the field are similar. So most of the cracks that we see in real life, we're able to pick up in the field, and the only cracks that weren't there in the field were generally the more minor cracks in the model. And so here we've got quite a complex set of movements which we think actually occurred, where we've got definitely settlement, but also some translational movements of the pier as well in one case. Okay, so moving on to the last of the modelling features that I wanted to cover today, modelling reinforcement. Since LimitState Ring 3, it's been possible to add reinforcement, and that can be added either on the surface of the intrados or extrados, or at some depth within the masonry. Now, in terms of the mathematics, it makes very, very affects the mathematics only in a very, very slight way. So all that we basically have is, in addition to the crushing of the masonry, we also have potentially a compression force and a tension force, which is carried by the discrete reinforcement. There are, however, some assumptions that you need to be aware of. The most important of those is that we're assuming that reinforcement yields in a ductile manner, and that the overall behavior of the masonry is largely unchanged. So the overall behavior of the bridge is presumed to be similar before and after adding reinforcement, i.e. we don't get any brittle failure modes that you might associate, for example, with heavily reinforced concrete. And then the middle one there, we're assuming that there's no debonding between the reinforcement and the masonry. Okay, so in terms of validation, before I get onto this, what I'll just show a very simple example. Which will allow you to gain confidence in the implementation. So here we've got actually, it looks like an arch, but it's actually a beam. If I click solve, then you get the predicted mode of response. The calculations for this example are included in the manual, and you can demonstrate to yourself that it's doing the right thing. So you can plot the shear force diagram now, you can plot the bending moment diagram, and you can assure yourself that the values of the bending moment, the shear force, etc., are as you would expect using hand calculations. So that's the first thing. So the second thing is that we've verified the model also with laboratory tests. In particular, here we're highlighting tests done by the Transport Research Laboratory some years ago. They built and tested 5-meter span soil-filled bridges with and without reinforcement. So what I'll do is open up first of all the bridge without reinforcement. This is what it looked like, and the peak load obtained experimentally was 200, and with the analysis we get 198. Now this is clearly a multi-ring arch, so we've got relative movement between adjacent rings. We've got these diffused hinges that are characteristic of multi-ring arches, and we can see from the thrust line that we've got the majority of the work being done actually by the bottom ring of the masonry. So the question is, can we enhance the capacity of this structure by putting in reinforcement? And the way we do that in the software is, first of all, we go to the overall bridge properties and we click this box saying that the bridge includes reinforcement. And the reason we've got a sort of a global box is just because many of the property editor panes will have a lot more information when reinforcement is present, and we don't want to that to get in the way when you don't have reinforcement. So that's the first thing. So now when I click on a contact, then I have more details in the contact pane there. So I have reinforcement depths, reinforcement forces, shear capacity, and so forth. So what I can do is I could select all the contacts where reinforcement is going to be added manually, and then add the reinforcement. In this particular case, what they actually did is they embedded reinforcement at a depth of 19 millimeters, and so I could specify that. However, there is actually a tool, a select tool, which allows me to select all those contacts at the same time. So that's a much easier way of doing it. And what I can do is actually enter the properties of the reinforcement, which in this particular case is to give a force of 149.3 kilonewtons in tension and in compression. And the depth of the reinforcement is, as I said before, 19 millimeters. So now what I have, if I zoom in, is actually an embedded reinforcement element. And if I click Solve Now, I get a new adequacy factor up from 198 to 325 kilonewtons. And actually, the reinforced bridge peak load was very close to that. It was 320 kilonewtons. So you can see we've got pretty good correlation. And what I can do now is I can show the bending moments that's been carried by the section and the shear force, etc. I could show the line of thrust. However, when you've got reinforcement, the line of thrust is much less useful. And I'll just show it. It actually gives you a warning now that it may not be particularly useful. And the reason it's not useful is because the line of thrust will lie outside the thickness of the ring involved. So you can see actually the thrust line for the bottom ring is now outside the thickness of the bottom ring. But you can view it if you want to. Okay, I think that's pretty much everything I wanted to cover on reinforcement. Let's just go back to the presentation. Yeah, so just to wrap up then, three things I've focused on today. First thing, software does allow local details to be modeled. So for example, partial ring separation, but it could be partial mortar loss or a variety of other issues. Second thing is support movement mode allows two things. One is potential load paths under working loads to be explored, and secondly allows us to investigate the likely causes of existing cracks. So what abutment movements, for example, are likely to have led to what we see in the field. And then the third is to say that in the current version of software, we can now add reinforcement. Quite a useful feature, although you do need to be aware that it assumes ductility, and you need to be sure that whatever reinforcement you do put in will allow that ductile failure mode to be retained. Okay, so moving on then to questions. If you have any questions, if you can just type those into the chat box, and I'll pick those up as soon as you do that. Okay, one question. Mentioned motor loss. How do we do that? Yep. Go back to the software. If I just move away from the reinforced arch and just click find something very simple. This is the masonry arch that we get using all the default parameters. So you can see 4-hinge mechanism. Now, let's suppose this bridge was over a stream. What I could do is I could, for example, model mortar loss just in those regions. Let's say it was quite severe mortar loss, 100 millimeters. So the previous adequacy factor was actually a multiplier on a 1 kilonewton load. In other words, it's a failure load of 455 kilonewtons. With the mortar loss, that's gone down to 372 kilonewtons. So it's very simple to do that, and it's likely to be significantly more realistic than assuming uniform mortar loss throughout. That's likely to be over conservative. So it's a very nice way of building in the features that you actually have in the bridge in front of you, rather than a notional bridge which has more severe defects. Okay, so just time for another question or two. Let's just see what we've got. Okay, I'm just looking down the list. Okay, I've got one here about reaction forces. How to get the reaction forces at the extremities. Well, if I solve again this model and I click on the contact at the extremity of the bridge, then I will actually get a shear force and a normal force. So effectively that gives us forces which we can alternately express in terms of horizontal and vertical forces. Haven't mentioned it, but there's also a report which actually gives you a full list of all the forces. Actually, it's a little bit small on this monitor, but there are shear and normal forces and also moments for every contact in the structure. Okay, time for one more question. Okay, there's one here. I'm just trying to read it. Are the backfill properties considered in ring consistent with the actual backfill properties considered in the test specimens? So if we go to the the backfill area, we're asked to enter what are effectively geotechnical properties, so unit weight, angle of friction, and cohesion. And we also have on the right hand side the ability to switch off modeling dispersion and horizontal passive pressures. But assuming you keep those active, then what's happening is that the unit weight and the angle of friction are used to calculate the passive pressures. Now, the passive pressures are those which have been validated in numerous experimental studies. So actually the first version of this software was developed in the 1990s in parallel with an extensive series of testing on laboratory scale bridges. So the results that you get from the software have been validated against laboratory tests, and we'll make sure that whoever asked that question is sent a list of papers and the like, which outline that in a bit more detail. Okay, there's another question, for the final question we've probably got time to do. How to account for axle liftoff. So if you have a very sort of curved profile, then there's a danger that not all the axles in the vehicle will be applied to the structure. The way you can do that is simply to increase the loading on, for example, 2 of the axles and reduce the loading on the 3rd axle. So it's possible to do it in a manual way. The software isn't linked to any given code of practice. So I'm aware that different codes in different countries approach this slightly differently. So you'll need to look at the details of the code of practice that you're working to see how best to incorporate that effect in the software. Okay, I think we're running short of time, so I'm just going to hand you back now to Tom Pritchard, who will just wrap things up.
Thanks, Matthew, and thanks everyone for listening today. As Matthew said, we're now near the end of the webinar, so we hope you found it informative and useful. For those of you who are current users of the software, we hope you learned something new about it, which maybe you didn't already know. And as we mentioned at the beginning, if the webinar has prompted any questions, then do please get in touch with us via info@limitstate.com or on telephone during UK office hours. For those of you who aren't users of LimitState Ring at the moment, we would get in touch in the next few days just to get some feedback from you, find out if you have any further questions, and see whether you think LimitState Ring might be useful for yourselves. Everyone may also be interested to know that we have a number of forthcoming webinars covering all the LimitState product range, some of which, like this one, will focus more on particular problem types and applications. So please do look out for those. We'll send out event notifications in advance by email and also post it on our website at limitstate.com/events. There are also a number of other webinars which are available to view on our YouTube channel, which is youtube.com/limitstatesoftware. So again, thank you all for taking the time to join us today, and we hope to see you all again for one of the future sessions. Goodbye.